All right, good afternoon, everyone. My name is Manesh Patel, and we'll get started with the third module in our series in just a moment. We will be recording this module, so please keep your microphones muted unless you are called upon. As a reminder, to better get to your questions, please do type them into the chat, and the staff will get to them as soon as they can. Do not forget, you can also email your questions into our unit email address as well. And if you run out of time to answer questions verbally after each presentation, we will try and get to them at the end of the module. Today, we'll be tying into what was presented in the two prior modules and apply that information to reviewing projects. So we have how to review a project 1, which will be presented by Peter Pliantos, along with myself. And we have how to review a project 2, which will be presented by Lisa Schaefer. After, we will administer quiz 3 along with the review of the quiz before we dismiss you for the day. So let's get started. I, along with Peter, who will take over in the second half of this presentation, are going to be going through part 1 of how to review a project. This presentation came about because our review of approved projects during compliance audits showed that projects were being approved even though the calculations and stormwater management reports submitted for local approvals did not comply with the stormwater management rules and the local stormwater control ordinances. Therefore, should these projects fail, the municipalities involved would be in violation of their respective permits. So here are the goals of this presentation, which are by no coincidence the goals of a successful project review. We want reviewers to be able to identify the design and performance standards that must be met on site, review applications for compliance with green infrastructure, stormwater quantity, stormwater quality, groundwater recharge standards, and review BMPs for compliance with the design criteria in the BMP manual. The information required in the stormwater report is specified in the stormwater control ordinance, and checklists are available to help with the review. The reviewer must make sure that any information found missing from the report must be added before approval of the project. The checklist found at this link in the TRA guidance document can help with your review of the report and help to just organize your observations and comments. Now, we're going to look at what the reviewer needs to be looking for in the actual stormwater management report. The first step in the project review is to check if the application package is complete. All the items that are listed here must be part of the application. So pre and post construction site plans and grading plans are essential, as are the associated calculations and any drainage area maps. The details in the report section should match up with the information on all plan pages. Too often we find that some parts or even all of the stormwater report do not match the site and grading plans because the report was copied from another project. So the reviewer must also be aware of whether or not the permittee has a more stringent standard of what must be in an application for approval. If so, the reviewer should be looking at all that information. The township's adopted ordinance, which should be posted online, is also a great starting place to find what information is required to be submitted. Another issue that we see that should be checked right away is that the plans and reports should also be reflected in the maintenance plan so that the BMPs will continue to function as they were intended to be. Too often, we see maintenance plans submitted that were copied from other projects and do not match at all the project that was submitted. So, like I just said, it is important that the reviewer checks that the site description matches up with the plans. The drainage and discharge points all need to be checked along with any change in pervious or impervious coverage. That includes regulated impervious surface and regulated motor vehicle surface for each sub-drainage area. And then also, soil information for the site should be included and be accurate. Lisa did cover this, the use of a web soil survey as a means for getting your soil information, and more guidance will be provided later on today. As a side note, print versions of county soil surveys are not always up to date, and they shouldn't be used as your sole resource. The report must include the following information regarding design and performance standards when it comes to what's required, along with any applicable variances, waivers, or exemptions, and how the standards will be met. Again, we find that this is often missing or does not match up to what is on the plan. So this is very important that the information is provided. The reviewer must be sure that the following calculations are included in the report. Time of concentration, as was discussed in Module 2 last Thursday by Peter, is essential to characterizing the site. Time of concentration must be calculated and included in the report. Some permittees may require this information be submitted on a CD so that it can be checked. No matter the format, though, it is important to include all of this information, including storm routings, hydrographs, the groundwater recharge spreadsheet, mounding analysis if it's applicable, and water quality calculations, and make sure it actually matches what's on the plans. So you saw this slide earlier in Module 1 in the overview presentation. Always check whether the project meets the definition of major development, because there could be a chance that it doesn't at all. Also, be sure to check the permittee's definition of major development in their ordinance, as it may be stricter than the department standard. One note here, you need to distinguish the different types of surfaces, whether it be regulated motor vehicle surface, regulated impervious surface, other pervious surfaces, and etc. in the report. Major development also includes all development that are a part of a common plan of development or sale that collectively or individually meet any one or more paragraphs that were shown on the previous slide at 1, 2, 3, 4, and 5. Projects that were undertaken by any government agency that would meet the definition of major development, but which do not require approval pursuant to the municipal land use law, are also going to be considered major development. We have previously discussed the definition of disturbance, which means the placement or reconstruction of impervious surface or motor vehicle surface, or exposure and or movement of soil or bedrock, or clearing, cutting, or removing of vegetation. There are certain maintenance and repair activities that do not qualify as disturbance in the stormwater management rules, however, as they are minor repair activities for the purposes of 7:8. You can see these activities listed here, some of which are milling, or paving, or resurfacing pavement, patching broken pavement, repair or replacement of median barriers, sidewalks, concrete curbs, inlets, manholes, and catch basins, repair or replacement of traffic, utility, and ITS structures on poles, repair or replacement of rail ties or sleepers, geotechnical investigation activities, and removal of accumulated sediment and debris from a channel. All of these do not qualify as disturbance in the stormwater management rules, for the purposes of 7:8. Also, we saw earlier in Module 1 at NJC 7:8-4.2, in the previous version of the rules, you can see the following text was included as part of 4.2a. It reads as, for purposes of this subchapter, major development is limited to projects that ultimately disturb one or more acres of land. In the NJPAC rules, this text has been removed. This change has now unified the applicability of the stormwater management rules between the state and municipal level. Once the reviewer has verified that the required information has been submitted and is accurate, they can begin to actually review the design and performance standards. Plans and report must address the information that is listed here. This information is crucial to determining whether the project was designed properly. Information such as whether the project is discharging to a flood hazard area, a Category 1 waterway, a 300-foot riparian zone located within the same HUC 14 as the major development are often not included, and therefore they're overlooked during the review. This information may also determine whether or not the project requires input from other agencies, such as the NJDEP Land Use or even the Pinelands Commission. A reviewer must ensure the proposed design complies with the design criteria established in the BMP manual, which in turn ensures the design meets the design and performance standards of the rules. If something is an alternative design or method of calculation, the department must be notified of the approval. Along with the other standards, reviewers must ensure the BMPs follow the green infrastructure standards. And for this, the BMP manual provides the design criteria and considerations for the individual types of GI BMPs. If the reviewer did allow for waivers or variances, they must be sure that they were applicable. Can waivers or variances even be granted? It's really not a straightforward answer, and to resolve this somewhat gray area, it's been better defined. So NJAC 7:8-4.6 set forth the conditions that would warrant the granting of a variance by municipality for a major development project. The rules are intended to ensure that municipalities are not granting variances under inappropriate circumstances. Municipalities do not have to grant variances, and they do not have to create a mitigation plan if they do not plan to grant variances. But if they do, they must create a mitigation plan that allows the evaluation of mitigation projects that are suggested for applicants, allowing for the consideration of projects that are submitted by applicants as is permitted at 7:8-4.6. Now, there must be a demonstration that it is technically impracticable to meet one or more of the design standards. The only allowable variances are for engineering, environmental, or safety reasons, and they have to be spelled out very clearly. Cost cannot really be a factor here. And one thing to note here, the approval of a variance shall apply to the individual drainage area and design and performance standard. There's a lot more to the mitigation requirements that must be met to obtain approval of a variance. Mitigation must be part of the municipal stormwater management plan and follow these new requirements. It must be selected from the municipal list of mitigation projects. or it could be proposed by the applicant if it meets the criteria for the municipal mitigation plan. It must be approved no later than the preliminary or final site plan approval. It must be located in the same HUC 14. It must be constructed concurrently or prior to the major development. It must meet the green infrastructure standards. And the entity assuming the responsibility of maintenance for the project must submit a written agreement to the review agency. And lastly, the approved variance must now be submitted to the county review agency and the NJDEP within 30 days of approval. Mitigation is required to receive a variance from the green infrastructure standards, but be aware that certain BMPs cannot be used as mitigation measures and that there are minimum sizing and drainage area limitations. Note that vegetative filter strips and grass swales are excluded as mitigation measures, and they don't address quantity control and groundwater recharge. GIBMPs that are used for mitigation need to be sized to manage the water quality design storm at a minimum and are subject to the specified drainage area limitations. Variances from the other standards are as shown on this slide. Note that there is no waiver or variance allowed for groundwater mounding. That's because the steps that are listed in Chapter 13 of the BMP manual make clear that if the selected BMP fails to pass the groundwater mounding analysis, another BMP must be selected and assessed, meaning that a whole redesign will be required. The reviewer should also be able to determine whether exemptions exist on site. The following exemptions may be granted if, and this is crucial, if the vegetated areas that were temporarily disturbed to conduct the project are to the maximum extent practicable revegetated with native, non-invasive vegetation upon completion of the project. And these exemptions are construction, reconstruction, or repair of an underground utility line or cable, or its supporting infrastructure, such as conduit, junction boxes, and manholes. Construction, reconstruction, or repair of an above-ground utility line or cable, or its supporting infrastructure, such as poles and towers. Construction, reconstruction, or repair of a public pedestrian access, if made of permeable materials, and no greater than 14 feet wide, a maintenance of a dam, and public safety improvements undertaken by a public transportation entity, which will include installation of guide rail systems, provided that any pavement utilized consists solely of permeable material, installation of traffic, utility, and ITS structures on poles, including sign structures, installation of railroad line side signaling systems, and rockfall mitigation activities that do not result in a net increase of regulated motor vehicle surface or impervious surface. These exemptions can be found at NJAC 7:8-5.2D. Finally, the reviewer may allow waivers to be granted for the enlargement of a road or railroad, or the construction or enlargement of a public pedestrian access if the requirements here are met. They're as follows: public need for a project that can't be met any other way, design and performance standards met to the maximum extent practicable. Meeting the standards would require condemning existing in-use structures. The applicant does not have and cannot get rights to other lands for mitigation. These specific exemptions were discussed earlier in Module 1. Water quantity at 7:8-5.6b 1, 2, and 3. They're exempt if the discharge from the major development will not result in additional flood damage below the point of discharge in the tidal flood hazard area, excluding the volumetric reduction standards, which still need to be met in the tidal flood hazard area. Water quality is exempt if the site has a NGIPTES permit with a specific effluent limit, and groundwater recharge is exempt for previously developed areas and an urban redevelopment area. It is important that the reviewer is aware of what urban redevelopment exemptions are and where they can be applied. Urban redevelopment exemptions can only be granted to previously developed areas of a site. So the existence of woody vegetation is a telltale sign of whether this exemption can be granted. If the reviewer finds that woody vegetation has returned to areas of a previously developed site, the exemption is not going to be allowed. The reason being is that removing woody vegetation, putting new construction over this portion of the site will result in a loss of groundwater recharge. And then the reviewer can check the NJGeoWeb to determine whether the rest of this information on this slide is applicable to the site. Moving on, the next thing the reviewer should be looking at is if the applicant is meeting the design and performance standards using green infrastructure. The rules require that the design and performance standards are to be met using green infrastructure. The rules require that green infrastructure BMPs be used to address the requirements for groundwater recharge, stormwater runoff quantity control, and stormwater runoff quality. Subsection 5.2 of the rules includes 3 tables, and they list those BMPs that may be used to meet the design or performance standards. The tables found there specify information on how each BMP may be used. Table 5.1 coincides with Chapter 9 of the BMP manual, which are the GI BMPs. And they include cisterns, dry wells, grass swales, green roofs, GI MTDs, pervious paving systems, small-scale bioretention systems, small-scale infiltration basins, small-scale GI sand filters, and vegetative filter strips. Some of these BMPs cannot receive runoff from motor vehicle surfaces and therefore do not address water quality. And those are cisterns and green roofs. Others don't offset the discharge of stormwater runoff from the 2, 10, and 100-year design storms, so they cannot meet the quantity control requirement, like dry wells. And not all MTDs are considered GI, but the ones that are considered are included here in Chapter 9. These MTDs have a vegetative or soil component that meet the GI definition. And lastly, these small-scale systems listed here have a limited drainage area that they can treat compared to other BMPs. As you can see, the column on the left includes the name of the BMP, and the column on the right includes the maximum contributory drainage area. So for example, if you are using a dry well, the maximum contributory drainage area is going to be 1 acre, MTDs 2.5 acres, and so on. Note, we are only talking about MTDs that are approved for GI. In the past, we've seen projects that propose to design 2 small-scale GI BMPs that each have drainage areas just less than the maximum allowed contributory drainage area, side by side, in a corner of the site, so as to try and get around the drainage limitation. However, a design like this is not going to meet the GI definition because GI means a stormwater management measure that manages stormwater close to its source. The design of small-scale GI BMPs shall be distributed throughout the site and manage the runoff closer to the source that is generating the runoff. As you can see from the first diagram, the GI BMPs are all clustered together. The second diagram shows two large-scale BMPs in proximity of each other. These BMPs would need to be spread out from each other to cover the entirety of the runoff of the site. Chapter 10 BMPs can be used to address stormwater runoff quantity control. These BMPs can have larger contributory drainage areas than the BMPs that were listed in Chapter 9. And these Chapter 10 BMPs include large-scale bioretention systems, large-scale infiltration basins, large-scale GI sand filters, standard constructive wetlands, and GI wet ponds. Note that though I said they can only address quantity, these BMPs may only be used to meet water quality and recharge if a waiver or variance is granted. BMPs in Chapter 11 are non-GI, and they always require a waiver or variance before they can be used. It's not anticipated that these BMPs will be used much in the future because of what is required in order to grant a waiver or approve a variance, but as for some of the BMPs that are noted on this table, blue roofs don't have a reuse component, and extended detention basins are typically large and require additional treatment to meet water quality standards. The majority of MTDs currently do not have a soil or vegetative component, so you would find them here in Chapter 11. And then you see non-GI sand filters, subsurface gravel wetlands, and non-GI wet ponds to round out Chapter 11. The next thing the reviewer needs to look at is stormwater runoff quantity control. Water quantity impacts must be addressed to not only prevent increased flooding due to development, but also to avoid increased flow rates, which can significantly degrade water bodies downstream from a site. In Module 1, we covered the different options a designer can choose to follow. I'll briefly go through the options to meet water quantity control, as we have found this to be done incorrectly in many of our reviews. It is important to note, though, that the reviewer must make sure that all points of discharge from the site must meet the water quantity control standard, and if not, then the project is not going to be compliant. So let's begin with taking a look at topography. Topography is very important in identifying where the stormwater flows, and it is required to determine drainage areas and the time of concentration. Reviewers should be able to find the topography information on the plans and make sure that it's accurate. This, in some cases, may even require the reviewer to physically see the site as well. It's often difficult for us to find drainage maps in these stormwater reports. We also see situations where the drainage calculations in the reports do not match up with the drainage maps in the plans. We need to see existing and proposed contours. We need to see the point of analysis, time of concentration flow paths, and the drainage area to each point of analysis. The reviewer must be sure that the data used in the calculations matches the various maps and plans. This information must also be included on the drainage plans as well. It's very important to understand that each drainage area needs to be calculated separately. The reviewer should see the following calculated separately for each drainage area and must check the calculations for each drainage area. You should not assume that if one calculation is correct, then the rest are correct as well. So here's an example site. The flow was evaluated as sheet flow directed primarily in a southerly direction. However, we received complaints of flooding along the road lying to the east of this project and from the area northwest of the project. It was determined that the drainage areas were not delineated correctly. Whether or not that was due to an incorrect evaluation of the topography, that's unknown, but this shows why it's important to properly evaluate it and delineate drainage areas. To prevent those issues from occurring, the reviewer must verify that all drainage areas are outlined correctly, the proper time of concentration flow path is used, and the time of concentration is calculated properly. The reviewer needs to make sure that any natural ponding on site is included in the model. This is often overlooked, and ignoring it for the existing condition means the allowed proposed volumes will be larger than they actually should be. So on that same example site that was shown a couple slides ago, there was a 6-inch deep ponded area within the shape that's depicted here. This was ignored, and the basin was made significantly larger than was needed. If there are any questions as to whether areas of ponding exist on site, and it cannot be determined from the photos of the site, you may just have to go there in person and see the actual site. The reviewer should be checking land cover next. Land cover should be clearly marked on the plans and be specific to what the land actually is. It should also include any existing BMPs that are on site. The reviewer must verify that the plans and cover descriptions in the report match what is actually on the site. Aerial photos can be used to make sure the most pervious cover that existed in the past 5 years has been used in the calculations. Again, it may be necessary for the reviewer to verify land cover conditions in person to make sure that they have been accurately described. Lisa has gone through how to determine soils, but just to reiterate, it is important to make an accurate determination of the soil types on site. The type of soil greatly affects the functionality of a BMP. So again, the reviewer can find soil info at the NRCS Web Soil Survey webpage. That's at the link provided here. If information on the site's soils cannot be found, use the methods found in Chapter 12 to determine the hydrologic soil group, either from the default HSG method or from soil testing. Making sure that the soil data for the site is accurate is a critical part of the review process. Inaccurate soil information can make or break a stormwater BMP, so a good practice generally is to review soil testing first. The rainfall depth and intensity information should come from these sources. You will need to make sure the current precipitation adjustment and future precipitation change factors are appropriately applied for the 2-year, 10-year, and 100-year storm events using these tables on the slide, which are also found in Chapter 5 of the BMP manual. NRCS has developed distributions for New Jersey, including NOAA C and D, which the BMP manual requires use of. These are already built into many stormwater modeling programs, such as HydroCat. So the reviewer should check that the correct distribution is selected, dependent upon where the site is located. The reviewer should next look at time of concentration. Information on how to calculate it can again be found in Chapter 5 of the BMP Manual and the National Engineering Handbook. We also need to determine if the time of concentration in the pre-construction is appropriately calculated. We need to make sure that they are not underestimating this value. We need to make sure that the Manning sheet flow roughness coefficient is 0.4 or less for the time of concentration calculations. According to the NRCS, the maximum Manning's roughness coefficient to be used is 0.8 for woods with dense underbrush, but in New Jersey, we do not have those conditions, so the maximum Manning's coefficient for sheet flow would be 0.4. Peter did cover this in Module 2, and more of this can be found in Chapter 5. As a reminder again, you will need to use the current precipitation adjustment factor and future precipitation change factor tables that are found in Chapter 5 to calculate the travel times for current and projected storm events using the 2-year, 24-hour storm event, which will be used to calculate the P2 parameter. You can look back through the handouts for the calculations presentations for Module 2 for more information on the correct way to calculate time of concentration. So in summary, the reviewer must make sure that the sheet flow, shallow concentrated flow, and channel flow inputs are all correct. They must make sure that the proper time of concentration was used with the corresponding method. They must check the pre-construction time of concentration calculations, and the reviewer must now check the post-construction time of concentration calculations, as it is no longer allowable to be assumed. Curve numbers are associated with the NRCS methodology and are used to calculate the amount of runoff caused by a specific amount of precipitation. The reviewer must be sure that the curve numbers correspond with each specific area based on land cover and hydrologic soil groups. The curve numbers are based on a presumption of good hydrologic condition, unless the design engineer provides evidence showing different conditions. Again, this was covered in Module 2. Here's an example of what a land cover table might look like from an engineering report. You see here the land cover, the area of the cover, soil types, HSGs, and associated curve numbers. The reviewer must check these numbers and land cover types against what is shown on the plans. Sometimes you could see that they do not match up from the soil group to curve number. So always be sure to check to make sure they correspond to each other. In all, the reviewer must check that curve numbers are justified in the report. You can verify these in the National Engineering Handbook. The reviewer is responsible for making sure the chosen values are reasonable and accurate. There are 2 hydrographs for New Jersey, the SCS and the Delmarva. Typically, the SCS unit hydrograph is used outside of the coastal plain region, and the Delmarva is used inside the coastal plain region. However, this does not apply if coastal plain conditions do not actually exist, nor for sizing MTDs. So, as the reviewer, you need to make sure the designer used the correct unit hydrograph. You also need to make sure that they use the same one in the pre and post-construction conditions. The next thing you'll want to check is the runoff routing. So, like we talked about before, the pervious and impervious areas need to be routed separately. Weighted CN cannot be used because it can greatly underestimate the total volume of stormwater runoff. So when reviewing the hydrograph printouts, you need to make sure that a weighted CN was not used. In addition to that, because there are multiple sub-drainage areas, like pervious and impervious, being routed to a single point of analysis, these sub-drainage areas need to be combined to determine the total peak flow rate at the point of analysis. Now, and this is important, you cannot simply arithmetically add the peak flow rates of all the sub-drainage areas to get the combined peak flow rate because of timing, since the peak flow rate happens at different times for each sub-drainage area. So in the hydrology software, all sub-drainage areas need to be routed to the appropriate point of analysis for a single combined hydrograph. Now, moving on to something that was briefly touched at the beginning of this presentation, if there are existing depressions on a site, meaning a place where water will pond before overflowing, they need to be modeled as existing basins. So as the reviewer, if you identify any depression storage areas on a site, you need to make sure that they're included in the model. Not including them can affect the existing time of concentration and ultimately the peak flow rate. These depressions and high permeability soils provide stormwater management benefits that need to be considered. In general, this is the procedure that should be followed to model existing depression storage in the middle of a site. First, model the depression area as a basin, meaning there will be sub-drainage areas going to the depression, and the depression will be modeled as a pond using the existing site characteristics. Next, you would calculate the time of concentration from the depression outlet to the point of analysis. This time of concentration will be used as the lag time between the depression and the point of analysis. Now, what exactly does that mean? That means the depression produces a hydrograph, right? Like any basin does. However, the stormwater still has some distance to travel before actually getting to the point of analysis, and we have to account for that. So in HydroCAD, for example, you can place a link between the depression/pond and the point of analysis. And in this link, you can add a lag time. That lag time will be the time of concentration that you calculated from the depression outlet to the point of analysis. So basically shifting the time of the hydrograph to the right to account for that travel time. And lastly, you will need to route the other sub-drainage areas that do not go through the depression directly to the point of analysis. So a combined hydrograph will, with the correct timing and peak flow, will be the result. Now, this is the same example as before. There was an existing depression storage area between these two contours that both the designer and reviewer missed. Now, as the reviewer, a good indication that an area needs further examination is the two contours of the same elevation next to each other. Because the question becomes, what's happening between the two 50 contours? Is it totally flat? Is there a random high point? Or like in this case, is there a random low point where ponding can occur? A site visit after a rain event is also helpful to determine if there are any depression storage areas. All right, so this slide is just digging into the model depression area step from before. To model depression area, you will need to do what you do for every basin. Determine the time of concentration, calculate the stage storage data for the depression area, which is basically the storage volume of the depression. Model the outlet from the depression area, which we will go over on the next couple slides, and route the contributory drainage area to the depression area. Taking a closer look at what this would look like in HydroCAD, you have your contributory drainage area, which is the green hexagon aka subcatchment, and your depression, which is the blue triangle, aka a pond. The subcatchment will have the drainage area, curve number, and time of concentration going to the pond, and the pond will have the depression characteristics to include the volume and any outlets. And taking a look at the HydroCAD summary, this depression was said to range from 49.1 feet to 49.7 feet with a total volume of 1,228 cubic feet. And the outlet was modeled as a 22-foot long broad crusted weir, which means that stormwater is basically spilling over the side of the depression at elevation 49.6. Again, all of this is based on existing site characteristics. So now I will hand it off to Peter, who will take you through the different options you can use to meet the stormwater runoff quantity control standards.
All right, thanks, Manesh. I will now share my screen. Just one more moment here. All right, so we will continue at slide 63. So after reviewing all the input parameters that Manesh just went over, the next thing to review is the output to see if it complies with any of the quantity control options. And these options were discussed in depth during Module 1. So the first option is to demonstrate that at no point does the pre-construction runoff hydrograph exceed, at no point can the post-construction runoff hydrograph exceed the pre-construction runoff hydrograph for the current and projected 2, 10, and 100-year storms. For more information on the calculation of the current and projected 2, 10, and 100-year storms, please refer to the stormwater calculations presentation for Module 2. It's important to note that there are 4 main variables that affect a hydrograph: the drainage area, the curve number, the time of concentration, and the rainfall depth and distribution. So if any of these variables change, it will change the hydrograph. Typically, the drainage area and rainfall depth and distribution will remain the same from pre to post-construction conditions, meaning the curve number, or CN, and the time of concentration are the biggest drivers when it comes to meeting this option. The CN value affects the peak flow rate and the volume of runoff. The higher the CN, the higher the peak flow rate and the larger the volume. As for time of concentration, it affects the peak flow rate also, along with the time of the peak flow rate and the steepness of the hydrograph. The lower the time of concentration, the higher the peak flow rate. Also, the earlier the time of peak flow rate, and the steeper the hydrograph. Generally speaking, the CN value affects the y-axis of the hydrograph, shifting things up and down. And the time of concentration affects the x and y-axis, shifting things up and down and left to right. So even if the CN is decreasing, if the time of concentration changes, that could cause the post-construction hydrograph to exceed the pre-construction hydrograph. Now here's an example directly from Chapter 5 of the BMP manual to demonstrate this option. So for a site located in Trenton, Mercer County, an approximately 2-acre paved parking lot is to be redeveloped as an office complex consisting of a new building, a parking lot, and landscaping. The existing lot has a slope of 1%. The redeveloped site will be regraded to a 5% slope for better drainage. And the landscaped area will not receive runoff from the impervious surfaces. Also, hydrologic soil group C soils are present. So in this example, we see a proposed redevelopment reducing the overall impervious area, but simultaneously increasing the slope of the impervious area to remain. So what do we think the outcome will be here? Well, a summary of the results from the modeling software is shown in the table on the right side of this slide. Please note, to correctly calculate the time of concentration, first, P2 was calculated by multiplying the NOAA rainfall depth for the 2-year storm, which is 3.33 inches, by the future precipitation change factor, which is 1.16. And that gives us a P2 of 3.86 inches. So based on the results in the table, it looks like the post-construction conditions are less than the pre-construction conditions because the peak flow rate and the runoff volume are less. However, when you export the hydrograph data into table format, which is converted into a chart here, you can see all the points on the post-construction hydrograph that exceed the pre-construction hydrograph, which are highlighted in yellow. You should similarly inspect all storm events this way, because again, this is just the projected 100-year storm. So this example dispels the common misconception that the reduction of impervious surface will automatically meet the quantity control requirements. Municipal review engineers must require that the design report include hydrologic modeling and hydrographs, even when the design engineer claims there is a reduction of impervious surface by the proposed development. All right, moving on to option number 2. Demonstrate through hydrologic and hydraulic analysis that there is no increase as compared to the pre-construction condition in the peak runoff rates of stormwater leaving the site for the current and projected 2, 10, and 100-year storm events, as defined and determined pursuant to NJAC 7:8, 5.7 C and D respectively, and that the increased volume or change in timing of stormwater runoff will not increase flood damage at or downstream of the site. This analysis shall include the analysis of impacts of existing land uses and projected land uses assuming full development pursuant to existing zoning and land use ordinances in the drainage area. So this option is a little more involved and requires applicants to submit a comprehensive set of analyses and documentation. However, if the analysis shows no increase in stormwater volume or peak runoff rates, and timing changes are due to the installation of BMPs to comply with 7:8 5.5 for the water quality standards, or 5.6D for the volumetric reduction standard, then no analysis of downstream flooding impacts shall be required, unless the review agency determines that the project will result in increased flood damages downstream of the site. And now, option 3. This option requires the use of BMPs to reduce the post-construction peak flow rates to 50, 75, and 80% of the pre-construction peak flow rates for the current and projected 2, 10, and 100-year storms, respectively. And even though this is the most common option, we still see a lot of mistakes, so let's go over it. So listed here are the various BMPs in chapters 9 and 10 of the BMP manual that can be used to provide quantity control. Please note that all of these BMPs are considered GI, which is a requirement to meet the quantity control standard. Additionally, Chapter 11 BMPs, which are not listed here, cannot be used to provide quantity control without a waiver or a variance because they are non-GI. So that would include BMPs like extended detention basins and non-GI wet ponds. Now, as I mentioned earlier, the stormwater report shall provide routing calculations for all subdrainage areas for all design storms. And the reviewer should check the unit hydrographs, the rainfall depths and distributions, the CN values and whether or not they were averaged, and the times of concentration. You should also check the summary to verify if exfiltration was used, which would be shown as discarded, and what the primary outflow is, which is the flow ultimately coming out of the BMP. Now, a reminder about exfiltration. Infiltration of the entire 2, 10, or 100-year storm is allowed only when the existing site conditions are such that no runoff leaves the site for the pre-construction condition scenario, thereby constraining the design to infiltrate 100% of the volume produced by the post-construction condition for the same design storm. In this case, the maximum storm that can be entirely infiltrated is the largest storm event with no runoff leaving the site in the pre-construction conditions. Exfiltration is also allowed if the volume of stormwater runoff to be fully infiltrated is required by law or rule implemented by the Pinelands Commission, the Highlands Council, or any other stormwater review agency with jurisdiction over the project. It's important to remember that if any of the BMPs will infiltrate runoff into the subsoil, a groundwater mounting analysis is required to determine the impacts of groundwater on the BMP and on adjacent structures. Therefore, if the design engineer is proposing an infiltration BMP but has not provided a groundwater mounting analysis, the reviewer shall ask the design engineer to provide it. And one key point regarding groundwater mounting. If the groundwater mounting height does not reach the bottom surface of the proposed BMP, then groundwater mounting will not have adverse impacts on the BMP. And the bottom surface of the BMP, in the case of a small-scale surface infiltration basin, would be the top of the sand layer. Now, often, the groundwater mounting analysis will show the mounding rising above the bottom surface of the BMP, as we see in the bottom left example, where the mounding curve rises above the sand layer of the infiltration basin. This means that the hydraulic conductivity will be decreased from the original design value. If this is the case, the routing calculations must also be adjusted to reflect this new, lower exfiltration rate. The primary peak flow rate will then need to be rechecked. And if the peak flow rate is too large, the basin size and/or outlets will need to be adjusted. The point being, it can be a very iterative process to get the mounding and the routing to work. And one last note about stormwater runoff quantity control. Small-scale GIBMPs in Table 5-1 of 7:8 can be used to provide both quality and quantity control with a contributory drainage area limit, while large-scale GIBMPs in Table 5-2 of 7:8 can be used to provide only quantity control without a contributory drainage area limit. For example, a small-scale infiltration basin that is designed to have the first outlet at the water quality design storm elevation may also have additional outlets, to include orifices or weirs, to attenuate runoff from the larger 2, 10, and 100-year storms. The important part is that the detention components must be situated in the same location as the BMP, either above the water quality design storm elevation or below the surface. A BMP with a detention component located downstream, outside of the basin's footprint, does not meet the design requirements as stated in the BMP manual. Now we move on to the volumetric reduction standard at NJAC 7:8 5.6D. The design engineer is required to show that the development meets the minimum volumetric reduction standards. There are more than one option to achieve this. The first option at NJAC 7:8 5.6D1 involves designing stormwater management measures to retain the water quality design storm using GIBMPs, which you can find in tables 5-1 and 5-2. However, when it is demonstrated that compliance with NJAC 7:8 5.6D1 is technically impracticable, as outlined in 7:8 4.6A1, or if the stormwater type is subject to 7:8 5.4B3, an additional option opens up to meet the volumetric reduction standard using alternative hydrograph requirements. These alternative requirements are: 1. The runoff peak flow rate of the water quality design storm from the site shall be less than the runoff peak flow rate of the water quality design storm from a drainage area equivalent to the size of the disturbed area of the major development with a woods cover type in good hydrologic condition and on HSG D soil. And then 2, the runoff hydrograph duration of the water quality design storm from the site shall be greater than the runoff hydrograph duration of the water quality design storm from a drainage area equivalent to the size of disturbed areas within the major development, again with a woods cover type in good hydrologic condition, and on hydrologic soil group D soil. For the purposes of this subparagraph, runoff hydrograph duration means the duration between the time that the runoff flow rate starts to be greater than 0 to the time that the runoff flow rate becomes 0. And we'll have an example on that soon. There is also the option to meet the volumetric reduction standard using NJAC 7:8 5.6D2. D2 may be used instead of D1 or may be used in combination with D1. Under D2, the applicant shall undertake one or both of the following. Oh, sorry about that. All right, yeah, so continuing here under D2. So the applicant shall undertake one or both of the following. 1, removal of impervious surface. The applicant can remove existing impervious surfaces. The total area removed must be equal to or greater than the impervious surface within the disturbed portions of the major development site. This helps reduce the amount of stormwater runoff generated by the development. Or the second option is off-site retention of stormwater. Alternatively, or in addition to removing impervious surfaces, the applicant can retain an equivalent or greater volume of stormwater runoff generated by the water quality design storm at an off-site location. It's important to note that runoff retained from storms other than the water quality design storm does not count toward meeting this requirement. Additionally, the volumetric reduction must occur within the same hydrologic unit code 14 or HUC 14 as the major development. However, if the applicant is a public transportation entity and can demonstrate that providing volumetric reduction within the same HUC 14 is technically impracticable, they may instead provide the reduction within the same watershed management area and as close as practicable to the major development. All right, continuing on. When submitting an application for a major development that relies on off-site measures, such as removing impervious surfaces or retaining stormwater runoff off-site, it's essential to include specific information and documentation. The application must be accompanied by detailed information about the off-site portion of the project. This includes specifics on the location, the extent of impervious surface removal, or the stormwater retention methods to be employed. Additionally, you must provide proof of permission from the property owners where the off-site work will take place. This ensures that the off-site activities are legally and logistically feasible. Without this critical information, the application will not be considered complete and will be ineligible for review and approval. Additionally, note that we will go over the last part of the volumetric reduction standards at NJAC 7:8 5.6 D3 in Module 4. It is specific to public transportation entities in certain circumstances. So part of understanding the volumetric reduction standards is understanding the term retention. A definition of retention has been added to NJAC 7:8 1.2. Retention means retaining the stormwater runoff that's generated from development by infiltration, evapotranspiration, or reuse of stormwater runoff without the discharge of the runoff directly or indirectly to surface waters or to a treatment works. Let's get into some examples from the new Chapter 14 of the BMP Manual to further clarify the volumetric reduction standard and how to meet it. In this first example, it is demonstrated that the project meets the volumetric reduction standard in accordance with NJAC 7:8 5.6 D1. The example states, a 2-acre wooded area in Morris County is to be developed. The site is on HSGC soil. The proposed development will consist of 1 acre of building area, 0.5 acres of parking area, and 0.5 acres of lawn area. The tested permeability of the subsoil is 2 inches per hour, which is suitable for an infiltration type BMP. Therefore, a small-scale infiltration basin is proposed to meet the stormwater quantity, quality, groundwater recharge, and volumetric reduction standard. So in order to meet the standard at NJAC 7:8 5.6 D1, using one small-scale infiltration basin, all runoff from the development for the water quality design storm will need to be contained below the first outlet orifice in the infiltration basin. So for the 1 acre building, 3,755 cubic feet of runoff is generated. For the half acre of parking area, 1,878 cubic feet of runoff is generated. And then lastly, for the half acre of lawn area, 134 cubic feet is generated. This sums to 5,767 cubic feet of runoff to contain below the first orifice of the infiltration basin. From the modeling picture to the right, we can see that for the water quality design storm, the peak elevation within the small-scale infiltration basin does not exceed the elevation of the first outlet orifice. Therefore, the full water quality design storm has been infiltrated and the volumetric reduction standard has been met. In this next example, an underdrained small-scale bioretention system is used to demonstrate compliance with the volumetric reduction standard in accordance with NJAC 7:8 5.6 D1I1 and 2. Remember that in order to have the option to use D1I1 and 2, it must first be demonstrated that compliance with NJAC 7:8 5.6 D1 is technically impracticable or is subject to NJAC 7:8 5.4 B3. With that demonstration made, we proceed. The first step is to identify the disturbed area subject to the volumetric reduction standard. In the case of this example, the major development disturbs 1.5 acres on a 2-acre lot. So 1.5 acres is the disturbed area. This option of meeting the volumetric reduction standards involves a comparison between the disturbed area of the site and a wooded area of equivalent size, 1.5 acres in this example. The wooded area shall be in good hydrologic condition and on HSG-D soil. From Table 9-1 in Chapter 9 of the National Engineering Handbook, the curve number, or CN, for a wooded area on HSG-D soil in good hydrologic condition is 77. And so a routing calculation shall be performed of the equivalent wooded area. With the routing calculation of the equivalent wooded area complete, there are two parameters of importance here: the peak flow rate and the hydrograph duration. As shown in the screenshot on the far right, the runoff peak flow rate is 0.237 CFS. And as shown in the center screenshot, the hydrograph starts at 1.5 hours and ends at 3 hours. As a result, the runoff hydrograph duration is 1.5 hours. For step 3, a hydrologic and hydraulic analysis will be performed for the post-construction condition of the major development. Note that in this example, the underdrains consist of perforated pipes connected to an outlet control structure. A 2-inch orifice is installed to control the flow from the perforated pipe, and an 8-inch discharge pipe is connected to the outlet control structure. The screenshot to the right shows that for the post-construction condition, the peak flow rate out of the BMP is 0.235 CFS. All right, so we got the peak flow rate in the last slide. All that is left for the post-construction condition is the hydrograph duration. The hydrograph of the discharge starts at 0.5 hours and ends at 10.5 hours, which results in a runoff hydrograph duration of 10 hours. With the runoff peak flow rate and runoff hydrograph duration determined for the disturbed area of the project and the equivalent wooded area, they may now be compared to see if the standard is met. As shown in the table, the runoff peak flow rate for the water quality design storm for the site is less than the peak flow rate for the equivalent wooded area. And the runoff hydrograph duration for the water quality design storm, or WQDS, from the site is greater than the hydrograph duration for the equivalent wooded area. Therefore, the major development meets the volumetric reduction standard at NJAC 7:8 5.6 D1I1 and 2. Here is some text from Chapter 14 of the BMP Manual, which provides some instructions relating to NJAC 7:8 5.6 D2. As an alternative to meeting the volumetric reduction standard, NJAC 7:8 5.6 D2 allows for the removal of existing impervious surface totaling an area equal to or greater than the impervious surface within the disturbed portions of the major development site. So I'll leave up this slide for around 10 seconds to give everyone a chance to read. All right, and this text rolls over into this next slide. So again, I'll give about 10 seconds so that you all can read. The next thing you, the reviewer, need to check is stormwater runoff quality control. The stormwater runoff quality standards are applicable when the major development results in an increase of 1/4 acre or more of regulated motor vehicle surface or the reconstruction of 1/4 acre or more of motor vehicle surface. And I would like to emphasize the bolded portion of the text here, that with the NJ-PACT rules, the reconstruction of 1/4 acre or more of motor vehicle surface now triggers the water quality standards. So for a new development, the proposed design must remove 80% of total suspended solids, or TSS, for the stormwater runoff generated from the water quality design storm from all new and reconstructed motor vehicle surface. 95% TSS removal is required for discharge within a 300-foot riparian zone, which we will discuss further in a couple slides. And although there is no numerical target, the stormwater management measures shall also be designed to reduce, to the maximum extent feasible, the post-construction nutrient load. It's important to note that these removal rates apply to each subdrainage area, unless the runoff converges on site. So what does that mean? This means that if all the runoff converges to one point of analysis, the design engineer may choose to overtreat some areas, say to 90%, and undertreat other areas, let's say to 50%, to achieve a weighted average of 80% TSS removal across the site. However, again, removal rates must be achieved for each point of analysis. You cannot average different points of analysis. Now let's also talk about total suspended solids, or TSS, for a second. It's a measure of the concentration of solid particles that are suspended in water as opposed to dissolved. This includes things like fine particles from tire wear, heavy metals, and hydrocarbons from brakes and emission, dust and dirt, particular organic matter such as leaves, and just general trash from the site. It's the things that make the water look turbid or cloudy. Stormwater management measures shall be designed to reduce the post-construction load of total suspended solids, or TSS, and stormwater runoff generated from the water quality design storm from all new and reconstructed motor vehicle surface. Now, what exactly is regulated motor vehicle surface? Well, per 7:8, it is defined as a net increase in motor vehicle surface, which is any surface, impervious or pervious, that is intended to be used by motor vehicles and/or aircraft and is directly exposed to precipitation. It also includes the total area of motor vehicle surface that is currently receiving water quality treatment, either by vegetation or soil, by an existing stormwater management measure, or by treatment at a wastewater treatment plant, where the water quality treatment will be modified or removed. At NJAC 7:8 5.5b, you will find the standards for TSS removal. Here at section B1, you see 95% TSS removal shall be achieved for stormwater runoff from any new or reconstructed motor vehicle surface that is proposed to be discharged within a 300-foot riparian zone or is discharged into an existing or proposed stormwater conveyance system that would ultimately discharge within a 300-foot riparian zone that's located within the same HUC 14. So in the previous rule, 95% TSS removal was required for stormwater discharge within a 300-foot riparian zone. The NJ Pact rule clarifies that discharge into a stormwater conveyance system, existing or proposed, which ultimately discharges within a 300-foot riparian zone located within the same HUC 14 as the major development, must also meet the 95% TSS removal rate requirement. At 7:8 5.5b2, 80% TSS removal shall be achieved for stormwater runoff from any new or reconstructed motor vehicle surface that wasn't covered under the conditions in the previous slide. There is also subparagraph I under 7:8 5.5b2, and it's the open bullet at the bottom on the slide. But this applies only to public transportation entities in certain circumstances, and we're going to dive more into that in Module 4. If modifying or removing water quality treatment for a motor vehicle surface, the project must maintain or increase existing total suspended solids or TSS removal unless there is a higher TSS removal that's required by 7:8 5.5b1 or 2. Overall, for NJAC 7:8 5.5a and b, these are the key points. Many of the points I've made in the last few slides are emphasized here. I'm going to give everyone a moment to read, and if you have any questions, please type them into the chat. So I'll just give like 15 seconds. All right, so let's go through an example which applies the definition of regulated motor vehicle surface and the amended NJAC 7:8 5.5b3. A site consists of 0.5 acres of building and 0.5 acres of parking area. The runoff from the parking area is currently discharged to a combined sewer system that is further connected to a sewage treatment plant that can remove TSS from the sewage flow up to 85%. The existing parking lot will not be reconstructed, but the runoff from the parking lot will be collected by a new storm catch basin and conveyed to the township's storm sewer system, which discharges to a nearby stream without any water quality treatment. So since the runoff from the existing parking lot is currently treated by a sewage treatment plant, but will be redirected to the township's storm sewer system under the proposed redevelopment, the parking lot will be considered an increase of regulated motor vehicle surface because the existing water quality treatment is removed. As a result, the parking lot needs to meet the stormwater quality standards. The 85% TSS removal rate provided by the sewage treatment plant is higher than the 80% TSS removal rate required under NJAC 7:8 5.5b2. Therefore, A TSS removal rate of 85% shall apply to the runoff from the existing parking lot for the proposed redevelopment. However, it should be noted that in many cases, the water quality design storm will overflow from the combined sewer system before reaching the treatment plant. In such cases, the required TSS removal rate can be calculated based upon the flow that actually reaches the treatment plant, which can usually be determined with assistance from the municipality or sewerage authority that operates the combined sewer system. We believe it will be helpful to provide some further clarification on reconstruction as it relates to the motor vehicle surfaces and disturbance. So when exactly does reconstruction apply, such as for work being done on existing pavement? In the amended definition of disturbance, the rules exclude milling, repaving, or resurfacing of existing pavement from the definition of disturbance. Accordingly, milling, repaving, or resurfacing existing pavement as maintenance for an existing development will not constitute reconstruction. However, for any work that extends beyond milling, repaving, or resurfacing in the case of a parking lot, that would be considered reconstruction. Here's another example. A 5-acre redevelopment site consists of 1 acre of woods and grass, 2 acres of non-motor vehicle impervious surface, including buildings and sidewalks, and 2 acres of parking area. Different redevelopment scenarios illustrate that different redevelopment proposals may result in different scopes of applicability of the stormwater runoff quality standards. So let's take a look at scenario 1. The proposed redevelopment will replace the existing buildings and sidewalk with a 2-acre warehouse, rebuild the 2-acre parking area at the same location, and leave the wooded and grass areas undisturbed. So in this scenario, where the 2-acre parking area is rebuilt, this scenario would reconstruct 2 acres of motor vehicle surface. Moving on to scenario number 2. The proposed redevelopment will replace the buildings and sidewalk with a 2-acre warehouse, resurface and repave the top asphalt of the existing 2-acre parking area, and the wooded and grass area will remain at 1 acre. So in this case, with the top asphalt of the existing 2-acre parking area being resurfaced and repaved, this scenario would not reconstruct motor vehicle surface. Under the quality standards, there is the new NJAC 7:8 5.5J. Stormwater management measures shall be designed to incorporate any additional measures specified in a TMDL approved or established by the EPA, unless otherwise required pursuant to NJAC 7:14A 25.6E. Now let's talk a little bit about what the water quality design storm is. We keep mentioning it, but what is it? Well, it's a design storm based on historic data that is specific to New Jersey. It's a relatively common and intense storm that introduces TSS into our collection systems and waterways. And more specifically, it is a nonlinear rainfall distribution resulting in 1.25 inches of precipitation in 2 hours. And let's take a look at what that means exactly. So as I mentioned, the water quality design storm is 1.25 inches shown on the y-axis over 2 hours shown on the x-axis. But remember, in addition to the rainfall depth, we need the rainfall distribution, which is how the rain falls. And the graph on this slide is the cumulative distribution curve for the NJDEP water quality design storm. It has a nonlinear distribution with a higher intensity in the middle, meaning that the rainfall starts light, gets heavy in the middle, and ends light as well. This nonlinear distribution is conservative because real storms have bursts of intensity, and this creates a higher peak flow rate. So let's take a look at the TSS removal rates for various BMPs. And also a note on the nutrient removal rates. So they can be found in Chapter 4 of the BMP manual. The nutrient removal rates are currently under review. However, the reason we look at phosphorus and nitrogen is because they are the most common nutrients and the most detrimental. They're naturally present in soils, plants, and organic matter, and stormwater runoff easily picks them up. Now, sometimes BMPs are used in series, meaning one right after another, like a treatment train to obtain the needed TSS removal rate. Because remember, not all BMPs give 80% TSS removal, and discharge within a 300-foot riparian zone requires 95% TSS removal. Also, some jurisdictions may require a higher removal rate as well. So the equation in bullet 3 can be used to determine the total TSS removal rate, with R being the total rate, A being the rate of the first BMP, and B being the rate of the second BMP. All right, so continuing on, here are some important notes when using BMPs in series. First, BMPs shall be arranged from upstream to downstream in ascending order of TSS removal rate. Second, BMPs shall be arranged in ascending order of nutrient removal rate. Third, BMPs shall be arranged by relative ease of sediment and debris removal. Additionally, you cannot use two of the same type of BMP in series because the downstream one will not be as effective. As mentioned before, nutrient removal is required for all major developments and shall be addressed to the maximum extent feasible. Some BMPs have nutrient removal capabilities, but the best way to handle nutrient removal is by source control. Please refer to Chapter 4 of the BMP manual for nutrient removal rates. As mentioned before as well, BMPs shall be designed in accordance with the BMP manual because there is specific design criteria that needs to be met for a BMP to merit the approved TSS removal rate. However, alternative designs may be submitted for approval if the design engineer can provide documentation demonstrating capability of alternative removal rates and methods. And these approved alternatives must be submitted to DEP. In summary, when reviewing the stormwater runoff quality component of a project, the reviewer must ensure the water quality BMPs chosen are adequate to achieve the required TSS removal rate, ensure small-scale GI BMPs from Table 5-1 are used unless a waiver or variance from NJC 7:85.3 is obtained, Ensure runoff from all drainage areas requiring water quality treatment is being collected and treated. Ensure BMP design meets the criteria under the applicable BMP manual subchapter. And ensure a deed notice of the stormwater BMP is submitted for approval and recorded in the county clerk's office prior to the commencement of construction. Now, there are some general design criteria for all water quality BMPs. This includes drain time and seasonal high water table separation. All BMPs must drain within 72 hours. Unless they are subject to pedestrian traffic, then the drain time is reduced to 24 hours for safety reasons. And most BMPs require a 2-foot separation from the seasonal high water table. However, under-drain BMPs only require 1 foot of separation from the seasonal high water table. And as for MTDs, the seasonal high water table separation is subject to the manufacturer's specifications. And here are the most commonly used water quality BMPs. Small-scale infiltration basins, small-scale bioretention systems, GI manufactured treatment devices, grass swales, and pervious paving systems. And now we'll take a closer look at some of these. So let's look a little deeper at the small-scale infiltration basin chapter, which is chapter 9.8 in the BMP manual. The first page is a summary page. The paragraph at the top describes how the BMP functions to remove pollutants, and the table right below that tells you which performance standards you can meet with this BMP. So in this case, you can use a small-scale infiltration basin to meet the GI requirement along with water quantity, quality, and groundwater recharge. And you get 80% TSS removal. Also, please notice that the table is shaded green, and the chapter title is also green. This is because all of Chapter 9 is green, Chapter 10 is blue, and Chapter 11 is black. This was done to make the BMP manual more distinctive from the previous versions. So because small-scale infiltration basins can be used to meet pretty much every standard, and they're a relatively shallow BMP, they're incredibly common. So let's talk about some specific design criteria for these BMPs, things you should look out for. So first and foremost, a small-scale infiltration basin must be designed to infiltrate the entire water quality design storm, hence the name, infiltration basin. It must also meet the infiltration permeability testing requirements in accordance with Chapter 12 of the BMP manual, which Lisa discussed in depth during Module 2. And the maximum depth of the water quality design storm in the basin is 24 inches. And this is what really dictates the footprint of your basin. Additionally, the basin must include a 6-inch AASHTO M6 or ASTM C33 sand layer. Also, the bottom of the basin must be level and uncompacted, so the soil erosion and sediment control plan should address how we plan to achieve this. Additionally, subsurface infiltration basins require 80% TSS pretreatment, and the design hydraulic conductivity of the most restrictive soil horizon below the basin bottom shall be between 0.5 and 10 inches per hour. These are all things to check for in your review. You want to make sure that they have all of these things. Now, what should you not see? Well, you should not see basins designed for water quantity control, but no outlet structure. How would they be controlling the larger storms in that case? Also, you should not see under drains or liners, since the water quality design storm needs to infiltrate, and it's an infiltration basin. Also, you should not be seeing topsoil or vegetation, since it's a sand bottom basin. And it's another bad sign if there's standing water 72 hours after the precipitation stops, because this will lead to impaired basin function and even failure. Now, here's a beautiful example of two small-scale infiltration basins. So, which one of these is functioning correctly? The correct answer is the top one. The bottom one has established vegetation and ponding by the headwall. Ponding like this is going to affect the hydraulic performance of the basin, and it may lead to structural concerns with the headwall because of seepage and erosion. Also, this stagnant water becomes the perfect location for mosquitoes and algae, all things we want to avoid. And how do we avoid this? Post-construction testing to ensure it was built correctly, and proper maintenance. All right, so moving on, we're going to look at next small-scale bioretention systems, which are also common because they can be designed to infiltrate, or they can be designed with underdrain if infiltration is not feasible. So again, shown here is the summary page, and notice that it says 80 to 90% TSS removal. Why is this? Well, because the TSS removal rate varies based on the soil bed depth and the type of vegetation. And it makes sense that a terrestrial forested community, also known as trees, provides more TSS removal than site-tolerant grasses, also known as shrubs and perennials. So you, as the reviewer, need to make sure that the chosen TSS removal rate lines up with their BMP cross-section and landscape plan. Now, as mentioned earlier, small-scale bioretention systems can be designed to infiltrate or designed with underdrain. They can also greatly vary in size, from small rain gardens to full-on basins. So one of the most important components of a bioretention system is the engineered bioretention soil. There needs to be a certain depth, like we just talked about, and the soil itself shall have a certain amount of sand, silt, clay, and organics, again, to merit that TSS removal rate. This soil mix should be specified on the plans, maybe on the landscape plan, maybe on the detail sheet, but it should be there somewhere. Small-scale bioretention systems also have specific design criteria for water quality depth, which is 12 inches, instead of the 24 inches we saw for the infiltration basin. And there's also design criteria for the bottom slope and the density of vegetation. And all this can be found in Chapter 9.7 of the BMP manual. So you, as the reviewer, need to make sure that this is met. All right, so before we finish this portion of the presentation, let's talk about infiltration criteria a little bit. Now, this criteria applies to any BMP designed to infiltrate runoff. This includes, but is not limited to, small-scale infiltration basins, dry wells, small-scale bioretention systems without underdrain, and small-scale sand filters without underdrain. Now let's take a look at what some of those criteria are. First and foremost, the soil permeability must be tested. It cannot be assumed. It must be tested in accordance with Chapter 12 of the BMP manual. Very important. After it's tested, a factor of safety of 2 must be applied to this field permeability to get the design permeability. And then this design permeability must be between 0.5 and 10 inches per hour. If it's less than 0.5, you cannot use an infiltration BMP without soil amendments. Once again, you must have at least 2 feet of separation from the seasonal high water table, maybe 1 foot for some of those underdrained BMPs. And the seasonal high water table elevation must be proven via soil testing as well. And after you know the design permeability rate and the seasonal high water table elevation, you must assess groundwater mounding impacts. So these are all things you should see as part of the stormwater management report for infiltration BMPs. Soil testing to determine the seasonal high water table and the infiltration rate, and a groundwater mounding analysis. If the design engineer did not provide this, you need to ask for it. Lastly, when reviewing plans, as mentioned before, there should be a soil erosion and sediment control plan addressing sediment and compaction impacts during construction, and there should be language requiring post-construction soil testing. 2 very important things. All right, so that is the end of this presentation. So I would like to thank everyone for your attention. If you have any questions, please feel free to reach out to the group or to Manesh or myself, and our emails are on the screen. And before we wrap up this portion of the presentation, again, if you have any questions, please add them to the chat, and Changyi will continue to respond to them as we move along with Module 3. Meanwhile, up next will be Lisa Schaefer, and she will continue to discuss how to review a project for compliance with design criteria in the BMP manual. But before we move to the next presentation, I'll check in with Changyi to see if it looks like we're taking a break, Changyi.
Yes, please take a 10 minutes break. Thank you.
All right, thank you.
Okay, the time is now 3:02. Welcome back, everyone, from your break. This is Lisa Schaefer, and thank you, Manesh and Peter. I'm sure the reviewers appreciate your coverage of the stormwater design and performance standards, and also that those who are not reviewers have a better understanding of just how important it is to properly review projects for major development. We've also had some great questions answered in the chat, so I believe a great big thank you is owed to our moderators. This presentation will hopefully add a little bit more to the reviewer's skill set. So the goals of this presentation are shown here, and by this, I just mean that we want reviewers to be able to identify the design and performance standards that must be met on site, what to check in sizing calculations for MTDs, and lastly, how to review the groundwater recharge calculations, and of course, to be aware of the safety requirements that should be present in a submitted design. So let's start with the first goal, review BMPs for compliance with the BMP manual design criteria. In Module 1, you learned that the BMP manual chapters are arranged in accordance with the order of the BMPs listed in tables 5.1, 5.2, and 5.3, which are directly in the rules. On the next few slides, a list of the respective chapters and the corresponding table from the stormwater management rules are listed side by side for your reference. Each subchapter of 9, 10, and 11 has a section titled Design Criteria. A BMP needs to be designed to comply with all of the specified design criteria. Otherwise, it doesn't merit the approved TSS removal rate required to address water quality. So let's look at the kinds of BMPs included in the stormwater management rules. So on this slide are the GI BMPs. Some can be used for water quality, provided the TSS removal rate listed in the second column in Table 5-1 is not 0, which is the case for 7 of the 10. Some can be used for quantity control, as noted in the middle column. And then there are those that can be used for groundwater recharge, as listed in the columns on the right, provided the 2-foot separation from the seasonal high water table is shown as measured from the bottom elevation of the lowest component in the BMP. Chapter 10 also includes BMPs that can be used for water quality, and their respective TSS removal rates are found in Table 5-2. So on the left are the BMP chapters for the GI BMPs that can be used for quantity control. The first 3 are like the big brother versions of the small scale systems found in Chapter 9. But take note that if you want to use these GI BMPs for water quality or groundwater recharge, you will need to get a waiver or variance. And Manesh covered some of the variance information earlier today, and you will see some more in Module 4. The Table 5-3 BMPs are not GI BMPs, and you will need to obtain a waiver or variance before you can use any of these for meeting the water quality or quantity control or groundwater recharge requirements. So here's some important highlights of the design criteria from some of the BMP chapters, but please refer to the full chapters for the additional details. Cisterns, if you want to design a cistern, the design storage volume needs to be at least that of the runoff generated by the water quality design storm. But the cistern also needs to be emptied by the reuse demand within 72 hours. Dry wells. The design of a dry well cannot exceed the runoff volume from the water quality design storm. Although a dry well cannot be used to treat runoff from motor vehicle surfaces, it can prevent clean roof runoff from being commingled with the dirty runoff from motor vehicle surfaces, such as a driveway, and it can therefore reduce the size of a BMP needed for water quality treatment. Green roofs do not address water quality as they are usually above vehicular surfaces in elevation. They create opportunities for evapotranspiration and can be used in volume reduction calculations. That section starts on page 13 of the chapter for green roofs. Plant selection must include an assessment of the hours of direct sunlight versus shade that the plants will receive, along with the effects of wind erosion, and don't forget to check if other structures will reflect light and heat onto the plants, potentially frying them. So please read the consideration portions of the chapter if you are planning or if you are reviewing a green roof design. All three of these BMPs can be used to meet the volumetric reduction standards through the collection of roof runoff and is discussed further in the new Chapter 14. Bioretention systems were covered in the previous presentation, so let's start with the key highlights for pervious paving systems. So if you want to design a pervious paving system, the storage volume needs to be at least equal to the runoff from the water quality design storm. Now, although there's no surface runoff from a pervious paving system, you need to use 98 for the curve number so the amount of precipitation falling on the pervious paving surface can be calculated. An infiltration BMP, all right, as we're going to go into small scale now, means one designed to infiltrate runoff into subsoil. So if the designer calls the BMP an infiltration BMP, it cannot be designed to have an underdrain system to direct runoff from being transmitted to the soil. Also, an infiltration basin cannot have vegetation on the bottom of the basin. If it has, it is not recognized as an infiltration basin. Small scale sand filters, all right, that are intended to meet the GI standards also cannot be designed with an underdrain for the same reason. So all three of the above GI BMPs can also be used to meet the volumetric reduction standard through infiltration of runoff or by matching the hydrograph duration as per Chapter 14. Vegetative filter strips. Well, not every piece of a vegetated area can be recognized as a vegetative filter strip. Only those vegetative areas that are designed and maintained strictly in compliance with the design criteria of the vegetative filter strip chapter can have the TSS removal rate listed in the chapter. The TSS removal rate and the associated filter strip length depend on the vegetation, the soil type, the hydrologic soil group, and of course the slope. There's figures and curves that you can use to find the TSS removal rate associated with these four parameters. Now, vegetative filter strips are not part of the BMPs that can be used to infiltrate runoff to meet the volumetric reduction standard, but it may be used to address the runoff hydrograph duration requirements, and they're found at NJAC 7:8 in subchapter 5.6 D number 1I. All right, we've also seen more developments using GI wet ponds to better meet the water quantity controls requirement. So let's discuss wet ponds in a little bit more detail. All right, we're going to start with the non-GI wet ponds, which can be used for water quantity and quality, but only when a waiver or variance from NJAC 7:8-5.3 is obtained. They have a minimum 0.25 acre permanent pool surface, and the minimum ratio of the permanent pool volume to the water quality design storm volume is 1:1. They also have a minimum drainage area of 20 acres, and they require very low permeability soils, all right, or an impermeable liner. But for GI wet ponds, they can be used for water quantity, they can be used for water quality, but only when a waiver or variance is obtained. The beneficial reuse of runoff can be used to meet the volumetric reduction standard. And in addition to the design criteria for the non-GI wet ponds, the GI wet ponds need to maintain at least the 10-foot wide area of native vegetation along at least 50% of the shoreline. They need to include a stormwater runoff retention component designed to capture stormwater runoff for beneficial reuse, such as irrigation. The volume available for beneficial reuse shall be equal to or greater than 1.25 inches of rain falling over the drainage area of the GI wet pond. And the reuse demand is based on the lowest volume need that would occur over any 3 consecutive days during the year. Now, beneficial reuse shall not cause the water level to be less than the permanent pool water level, and GI BMPs that infiltrate the water quality design storm runoff into the subsoil cannot provide the water quality design storm runoff to the GI wet pond for beneficial reuse. Okay, so the beneficial use of a GI wet pond is often to provide landscape irrigation. The method to estimating irrigation use shall be based on reasonable assumptions. So the designer just can't randomly assign a value, say like 1 inch per acre per day, to calculate irrigation use. And we have from the NRCS a published New Jersey irrigation guide, which provides one method to estimate the irrigation need. But if the designer wants to use another method, the submission would need to provide a well-recognized publication showing the method and the variables that were used in the calculations. And we'll work on guidance for those situations. But for now, we can consider them on a case-by-case basis. And please, municipalities should contact us for assistance in making these determinations. All right. Additionally, the antecedent water capacity can be found from the web soil survey. You're going to use the weighted average within the effective root zone depth of the landscape vegetation. The irrigation needed as beneficial use must be consumed by vegetation in 3 consecutive days. The evapotranspiration of the landscape area has been considered in the consumptive use, so therefore don't double count it. An evaporation loss from the wet pond surface can be counted as part of the beneficial use. All right, so let's move on to the safety requirements, and they're found in the rules in subchapter 6.2. So designs must follow the stormwater management rules regarding the trash rack and overflow grate specifications. This is also included as text within the illustration shown here in the DMP manual chapters. It's usually under the outlet structure information, and it's used to depict the requirements stated in the rules. So one thing you should note is that the rule amendments from January eliminated a minimum size orifice of 2.5 inches at the inlet to an outlet control. And pursuant to that change, this detail was updated. It's a subtle change, but I wanted to be aware of it in your reviews. There's also additional language, namely any flow control device, such as an orifice, weir, grate, or perforated pipe at the outlet of the stormwater management measure shall be designed to prevent the clogging of the flow control device while achieving the design and performance standards at NJAC 7:8-5.4, 5.5, and 5.6. And I believe Manesh covered this in the maintenance presentation from Module 1. So, when a wet pond or other BMP that has a permanent pool of water greater than 2.5 feet in depth is proposed, you also need to make sure that the design follows the rule requirements for the safety ledges. If not, then address this lack of information in your review letter. All right, so now let's talk about the design that includes a manufactured treatment device, or MTD. So some of this information is a little repetitive, but we often see incorrect sizing calculations in our reviews. Therefore, we're hoping the emphasis will inspire a little extra attention be given to MTDs proposed for a project. All right, under the stormwater management rules, there are 2 major categories of manufactured treatment devices. There's the GI MTDs and the non-GI MTDs. So a GI MTD shall infiltrate runoff into the subsoil and or treat stormwater runoff through filtration by vegetation or soil. An MTD that uses a biofiltration media and can be configured above ground and incorporates a tree box, a planter box, or shrubs, etc., would meet the GI definition. Any MTD with biofiltration media that would be placed below ground as a vault without any vegetation can be considered to be GI for New Jersey purposes only if the device infiltrates stormwater into the subsoil. Furthermore, the below ground device or vault would need to meet the New Jersey BMP manual soil testing conditions from Chapter 12, and that means the soil below the MTD must meet the minimum tested infiltration rate of 1 inch per hour, have at least 2 feet of separation from the properly tested or located seasonal high water table, and runoff would infiltrate into the subsoil. Now, the other category of MTDs is the non-GI MTDs, and they neither infiltrate runoff into the soil nor treat stormwater runoff through filtration by vegetation and or soil. So it's just a reminder that if the design proposes to incorporate MTDs to meet the water quality design and performance standards, then the designer must incorporate GI MTDs into the design unless a waiver or variance for using non-GI MTDs is granted. For all MTDs proposed to meet water quality in a project, they must be verified by New Jersey Center for Advanced Technology, and they must be certified by the New Jersey DEP. So I want you to remember from Module 2 that contributory drainage area, is defined as the area from which stormwater runoff drains to a stormwater management measure, not including the area of the stormwater management measure itself. Okay, so I missed a part there. Certified, verified and certified. All right, you can't use out of date MTDs, and you have to follow the sizing calculation in the letter. We have the listing here, and we have the maximum contributory drainage area. And as I just said, the definition does not include the area of the stormwater management measure itself. So we want to emphasize that the review engineer must read the certification letter before completing the review. That letter provides the calculation method to size and select the appropriate model of an MTD. The maximum treatment flow rate is calculated based on the peak runoff flow rate from the impervious surfaces during the water quality design storm. And of course, the certification letter also has other criteria and conditions of the certification pertaining to the MTD. So, for example, one certification letter states that the inflow pipe can only be a single pipe. And in that case, if the site plan showed 2 pipes directing flow into the MTD, then the MTD is not designed in accordance with the certification letter and therefore cannot receive the TSS removal rate that's stated in the letter. So because only specific MTD models from the MTD manufacturer were tested, the manufacturer's other models that are not listed in the certification letter, even though they're the same type, cannot be used to meet the water quality design and performance standards. Also, the MTDs were tested under specific configurations and installation specifications. So MTDs that deviate from the configuration or installation specifications cannot be used to meet the water quality design and performance standards. All right, so if the sizing requirement in the certification letter indicates that the sizing is based on the maximum treatment flow rate or MTFR and maximum inflow impervious area, the model selection shall be based on the flow rate and the drainage area, and whichever results in the highest minimum configuration shall be chosen. Every certification letter has a sample sizing calculation illustrating the choice of a particular model. So, with regard to the MTDs that were tested and certified that included vegetation in the MTD, You'll see in the certification letter the language shown here. One of the conditions requires the maintenance of vegetative cover at 85%. So you'll definitely need to see a maintenance plan that has preventive and corrective actions to maintain the vegetative cover at this level. And you'll also want to check the MTDs regularly to ensure that the vegetative cover is maintained satisfactorily, especially after dry spells and even periods of excessive rainfall. So there are other design criteria in the certification letters that a design must follow in order to receive the TSS removal rate. And this is another sample of the language regarding a GI MTD that is underground. It needs to be designed to infiltrate the entire water quality design storm in order to be recognized as a GI MTD and receive the 80% TSS removal rate. Okay, moving on. So MTDs are no longer sized using the rational method. The rules that were amended in July of 2023 specified that the NRCS methodology shall be used. So that's it. No more rational method. All right, example 5-9 in chapter 5 of the BMP manual demonstrates the necessary calculation. So also make sure the SCS standard dimensionless unit hydrograph is used and that the precipitation depth is based on the projected 2-year design storm. Remember to apply the future precipitation change factor from table 5-6 of the rules to the 2-year NOAA precipitation data or to the county rainfall data if that's what's being used to calculate the precipitation depth for the projected 2-year storm. So this example is sizing an MTD using NRCS methodology. All right, and it'll walk you through what's needed. So we have a 0.26 acre paved motor vehicle surface with a slope of 5%. The rainfall depth for the projected 2-year storm is 3.84 inches, and the hydraulically most distant point to the inlet of the GIMTD is 110 feet. Okay, so when using the NRCS methodology, you need to calculate the time of concentration, and the method is in example 5.1 in chapter 5 of the manual. And the example is found there and on page 33. It's also the formula that was on slide 29 or so of the calculations presentation. And as was stated earlier, we used P sub 2 for the projected 2-year storm in the TC calculation for the water quality design storm. Of course, there probably won't be much difference if we mistakenly use P2 from the current 2-year storm, given our drainage area is only a 1/4 acre. But then we have to calculate the maximum sheet flow length using the formula for the McEwen-Speece limitation from page 25 of chapter 5, and in this case is equal to 909 feet. However, the maximum sheet flow length should not exceed the McEwen-Speece limitation or 100 feet, whichever is shorter. So here we're going to use 100 feet. So for our stated flow path length of 110 feet, that leaves 10 feet of shallow concentrated flow. And as a result, T sub C is calculated to be 0.8 minutes. All right, now we're also going to use the SCS standard dimensionless unit hydrograph with a shape factor of 484. And you'll see that on page 27 of chapter 5 in the manual. And with all of this together, the modeling software calculates the peak flow rate for the water quality design storm is 0.82 cubic feet per second. Now, the next step would be to determine the size of the MTD. The selection of the model that's listed on the webpage will be based on the maximum treatment flow rate, MTFR, for a hydrodynamic type MTD, or the maximum allowable drainage area evaluation method and the MTFR evaluation method per the certification letter for the filtration type MTD. All right. GI MTDs are covered in Chapter 9.5, and Chapter 11.3 covers the MTDs that are not certified as green infrastructure for this type of calculation. Okay, so if you need to look there, please do. If you have questions, reach out. All right, this table shows the various models of a hypothetical GI MTD and the maximum treatment flow rate and the maximum allowable drainage area associated with each model. So, okay, both are used to size the model. All right, so we're going to look at the third column. The motor vehicle surface used is 0.26 acres in size. So we cannot use model M1 or M2 shown here because the area we need is larger than the maximum drainage area stated for these two models. That means we'll check the MTFR for the remaining models in the table. The water quality design storm peak flow rate for the motor vehicle surface was calculated to be 0.82 CFS. Only M7 has an MTFR that is greater than the calculated peak flow rate. Therefore, we shall select M7 as it has the highest minimum configuration. Okay, so far, these are things I've covered. All right, you've got to follow the BMP manual. Obviously, the others covered earlier using BMPs in series. You need to make sure you have the correct soil permeability testing for your infiltration BMPs. Of course, detention BMPs will have to calculate detention time correctly. Go to Chapter 5 for that. And our MTDs must be designed using the NRCS methodology. Okay. There's also something that you need to consider if you're swapping out an MTD for a different one. All right. And reach out to us if you're unsure about the sizing. There's been instances where a filter type MTD was replaced with a hydrodynamic MTD. And unfortunately, too small of a model was selected. And that resulted in serious water quality issues and flooding. All right. So let's move on to groundwater recharge. From the overview presentation, Peter covered the rule requirements found at NJAC 7:8 under subsection 5.4 B1 Romanet 1 and 2. All right, so it's here where the project is required to either demonstrate through hydrologic and hydraulic analysis that the site and its stormwater management measures maintain 100% of the average annual pre-construction groundwater recharge volume for this site, or infiltrate the difference in the projected 2-year storm runoff volume. So if the option to infiltrate the difference is selected, it's a relatively simple calculation, but it usually means a larger infiltration structure is needed, and that could mean a greater risk of failure, as well as a larger groundwater mound in the hydraulic impact analysis that is required. And review would make sure that calcs, of course, use the NRCS methodology and that show both the pre and post construction projected 2-year runoff volumes, and the curve numbers and the time of concentration should match the quantity and quality calculations used elsewhere in the modeling. So let's just do a really quick example. All right, so I'm using the NOAA rainfall depth, and I have the future precipitation change factor. In this case, it's for Somerset County, and we have the depth of the projected 2-year design storm. So with a precipitation depth of 3.93 inches, the projected 2-year design storm will produce an increase in runoff volume for the post-construction condition of 17,886 cubic feet as shown here. All right, to comply with the rule requirement, that's the target the design must achieve, provided it is also designed with everything else that's in the BMP manual. Okay, so let's move on. So if instead you select the first option, which is to maintain 100% of the pre-development groundwater recharge. You must use the groundwater recharge spreadsheet. And the reviewer will check both worksheets, which are the inputs for the pre and post development conditions that are then used to calculate the deficit, and then the evaluation of the proposed BMP on the second worksheet. All right, so this is the first page of the groundwater recharge spreadsheet, and the tab says the name. We will refer to this as annual recharge worksheet. The orange shaded areas are for user inputs. The gray areas are the outputs. All right, so let's look at the inputs required. So, of course, infiltration is not the same as groundwater recharge. Infiltration is only the process to allow runoff into the subsoil. For groundwater recharge, the runoff needs not only to drain into the subsoil, it has to pass the root zone. So the root zone is determined from the soil series selected. Therefore, soils in this spreadsheet play an important role in the calculation of the annual recharge and the recharge provided by the BMP in question. So I want you to notice that the total area, all right, matches from pre to post. And we'll get to the blue rectangle down here in a moment. But let's first talk about these inputs in the red boxes. All right, so the spreadsheet assigns annual precipitation based on the municipality. So of course, be careful when selecting the municipality. And next are the land covers. So as stated earlier, the volume of groundwater recharge is the runoff infiltrated into the subsoil and passed through to the root zone. In the spreadsheet, the land cover is used to determine how much runoff is infiltrated into the subsoil. So remember, it's the soil series that determines the depth of the root zone. So the spreadsheet will calculate the pre and post development annual recharge. The difference between them is the annual recharge deficit created by the proposed development. So here's some tips, all right, when using or reviewing the inputs of the spreadsheet. Okay, the land cover you select should also be reflected in your plans and hydrologic computations. And you'll have to know the acreage and the soil series. The sum of the acreage for all of the pre-construction land segments has to equal the sum for the post-construction land segments, just like those totals I had in those turquoisey squares 2 slides ago. Okay, so, but what about the soils in the inputs? So you're going to find the soil series from the web soil survey, and it's on the soil information tab where you find the hydrologic soil groups for the site. But in the event that the web soil survey does not provide the soil series, you may use the default values in the DEP's soil testing chapter. They're listed in table 12-2, all right, in chapter 12, and I believe that's page 10. For HSGA soils, the default is Fort Mott, and it's Nixon for HSGB soils. The default C soils in the past was Venango, but it's been updated to Reddington. Now, we also don't just use D soil to represent the soil series without recharge. The default D soil should be the soil series from the recharge spreadsheet that results in 0 groundwater recharge. So when you click the tab for soil down here, okay, you can find one and use it. Any of these that have blue arrows, okay, or others that have zeros in the highlighted like this, okay, may be used. So one last thing. If the land cover is impervious surface, it doesn't matter what soil series you use. The program automatically assumes no recharge on an impervious area. All right. So once you have all of the land segment areas and land covers selected for the soils present, the worksheet calculates the deficit created by the proposed project. So here it's 103,435 cubic feet. All right. And then let's go to the second worksheet. All right. We're going to go from here to here. All right. And that way we will evaluate whether the proposed BMP adequately addresses the deficit created by the proposed development. So it looks like this. All right. So once again, orange is for inputs and gray are the outputs. The red text on the right shows the status of whether the calculations are correct. All right, the three gray buttons on the left solve for ABMP to provide VDEF, solve for DBMP to provide VDEF, and default VDF and AIMP. They're not really used in the spreadsheet when you use the actual BMP design parameters to check whether the annual BMP recharge volume is equal to or greater than the post-development deficit recharge. All right, so next, I want you to take a look at this red box, all right, which is for the input to denote the BMP location. Since each different soil has a different root zone, the soil at the location of the BMP will be an important factor to determining the amount of runoff in the BMP that can pass the root zone. So therefore, the BMP location shall be the land segment where the BMP is to be located in the post-construction side of the input sheet, okay, the previous sheet. If the location of the BMP is not input, the default value is 0. And by that, the spreadsheet then uses an average root zone depth of all the soil series on the post-construction condition to calculate annual BMP recharge. All right, we'll address the other BMP design parameters in the other boxes in a minute. Oops, sorry. But let's talk about BMP location land segment. All right, so seg BMP is the variable to denote the segment in which the BMP is located. All right. We're going to talk about the variables now shown previously in the other red boxes that were on the bottom of the BMP calculations worksheet. So VDEF, which is the post-development recharge deficit, by default, it's the post-development annual recharge deficit from the first worksheet. However, there are instances in which it can have different values. So if you have two BMPs, each BMP will be responsible for a portion of the annual deficit from the first worksheet. So then you'll need two workbooks and split the annual recharge deficit between the two and separately calculate the recharge provided by the respective BMP in its respective workbook. AIMP, which is the post-development or post-D impervious area or targeted impervious area, is the size of the impervious surface that contributes the runoff into the BMP. All right, in some situations, not all impervious surface will contribute to a specific BMP. So like you might have the runoff from a part of an impervious surface directed to a wet pond, and that doesn't provide recharge. In another situation, you'll have more than one BMP, maybe two infiltration basins in two locations that have different soils. You would then also use two more workbooks and split the impervious surfaces between the two workbooks, make sure to input the right locations of the BMPs into their respective workbook. And then you're going to add the annual BMP recharge volumes from those two workbooks to check if it is equal to or greater than the annual recharge deficit that was originally calculated for the entire site. Now, for the parameters from the upper left corner of the calculation worksheet. ABMP is the BMP area for infiltration. The sides of a BMP, which are often sloped, are not counted for infiltration, so they're not counted for groundwater recharge. DBMP represents the BMP effective depth, meaning the max equivalent water depth achieved before overflow begins. If the BMP is filled with stone, we have to factor the effective depth by the porosity of the fill material. If the BMP has a slope, such as say in a bioretention swale, we're going to have to make adjustments to the effective depth by dividing the storage volume by the ABMP to get the averaged DBMP. All right, and there's more about other input parameters on the next slide. Okay, so we have dBMPU. This is the vertical distance from the vegetated ground surface to the maximum water level of the BMP. And it's positive if the maximum level is below the ground surface and negative if it's above the ground surface. I'll have some illustrations shortly. DEXC is the vertical distance from the vegetated ground surface to the bottom of the BMP. All right, so all right, let's look at some design scenarios to clarify what we mean, and there are pictures. All right, so this is an example of a BMP that has a vegetated bottom, which represents recharged BMPs like bioretention basins. The parameter dBMPU is the depth to the upper level in the BMP. In plain language, it's the vertical distance from the vegetated ground surface to the maximum water surface level in the BMP. If the vegetated ground surface is below the water surface, the value is negative, like in the figure shown here. The second input is the DEXC, which is the which is the depth of the lower surface of the BMP. So in plague language, it's the vertical distance from the vegetated ground surface to the bottom of the BMP. Now, in the present case, the vegetated ground surface is the bottom of the BMP, so DEXC equals 0. All right, and I'll get to the others where there's only vegetation adjacent to the BMP in a moment. Okay, we put all the other things on the slide because we want you to use this as a reference. All right, in these figures, these show another scenario where the bottom of the BMP is not vegetated, such as an infiltration basin or a sand filter. The top one is for shallow configurations, and the lower is something for a deep basin configuration. All right, in this scenario, the vegetated ground level is the ground level surrounding the BMP. The dBMPU, that is the vertical distance from the vegetated ground surface to the maximum water surface level in the BMP, right, is positive since the vegetated ground is above the maximum water level. The DEXC is the vertical distance from the vegetated ground surface to the bottom of the BMP, all right, which is the full distance from the bottom of the BMP up to the ground level surrounding the BMP. All right, lastly, these figures are for situations in where your BMP is underground, like a storage bed in a pervious pavement system or an underground infiltration basin. The top is for shallow configurations and the bottom is for deep ones. The dBMPU will be from the top of the gravel layer where the runoff is stored to the top of the ground level, and the value is positive. If the maximum water level in the gravel storage bed is not up to the top, then the dBMPU will be the maximum water level to the ground level. All right, the DEXC will be the distance from the bottom of the gravel storage bed up to the ground level. All right, we need an example. Okay, so we have a BMP in which the center area here is shown in yellow. It's designed to infiltrate stormwater over an area of 6,000 square feet. All right, this is a sectional view of that infiltration basin, but note again that there's no vegetation on the bottom of the basin. The dBMP is the maximum water level before the water begins to overflow. So from the figure, the maximum water level during the water quality design storm is at an elevation of 12.5 feet. Normally, the lowest orifice is set at this elevation. So therefore, normally, the dBMP would have been the distance between the maximum water level of the water quality design storm and the bottom. However, in this case, there's a little bit of variation. So from the outlet structure detail drawing, we see that the lowest orifice is at 13.36 feet in elevation, and that's between the elevation of the water quality design storm and the 2-year storm. So in this case, the orifice is set higher than the water quality design storm, and that is going to capture more runoff to provide enough runoff volume, hopefully to meet the annual groundwater recharge deficit. Knowing this, the dBMP is therefore 13.6 minus 12, or 1.36 feet. All right, and so let's look at our design inputs. The dBMPU is the vertical distance from the vegetated ground surface to the maximum water surface level in the BMP. The vegetated ground surface in this case is not the top of the berm. All right, it's the ground level surrounding the BMP, and that's at an elevation of 15 feet. All right. Since the maximum water level before overflow is at 13.36, the dBMPU, which is the vertical distance from the vegetated ground surface to the maximum water surface elevation in the BMP, is therefore 15 minus 13.36, which is 1.64 feet. The DEXC for this BMP, since it has an unvegetated bottom, is the distance from the vegetated ground level to the bottom of the BMP. So that's 15 minus 12, which equals 3 feet. All right, so as we calculated before, the BMP effective depth, or dBMP, is the maximum water level, which is the distance from the elevation of the first orifice to the bottom of the basin. The volume before the first orifice is 59,400 cubic feet from the report. And we can use this to calculate our ABMP, which is the BMP's infiltration area. So we know the effective depth is 1.36 feet, and the equation for the volume of a BMP is BMP area multiplied by the effective depth. So let's solve for the area. All right, and that gives us a result of 43,676 square feet. If this BMP had been designed as a bioretention system, the value for DEXC would be 0, since the BMP would have a vegetated bottom surface. And in that case, dBMPU would be equal to negative 1.36 feet. So for groundwater recharge, right, we want to remember these important rule requirements. You cannot recharge areas with high pollutant loadings nor industrial stormwater that has been exposed to source material. So the part of a gas station near the pumps should direct runoff away from a recharge BMP. And don't forget that all design criteria from the applicable chapter must be met. And you also have to address groundwater mounding. And Peter will cover that in Module 4. All right. So, all right, these are everything that we covered today. All right. And I really appreciate your paying attention. And if you want to reach out, feel free to contact me. And if you have questions during your review, give us a ring. All right. So, looks like we can move forward.
Yep. Thank you, Lisa. So it is now time for quiz 3. I think you all know the ropes by now, so I'll move through these first few slides fairly quickly. As I'm sure you remember, using a new tab or window, you have the option to follow the link that's shown at the top of this slide, which will take you to the training website where you will find the quiz links at the bottom. You'll also find the link for quiz 3 at the bottom of this slide here, which staff will also be pasting into the chat. Or you may use the camera app on a smartphone to scan the QR code that is found at the bottom right. Note that the QR code will also be posted in the chat by our staff. Once you click on the link for quiz 3, you will be directed to the quiz, which should now be open on SurveyMonkey. Do remember to make sure to click submit at the end of the quiz to get credit for completing it. You must answer every question before you can advance to the next screen and finally submit. And you may only take the quiz once. Now here's everything all in one place. Just a reminder, the quiz link is also in the body of the email that was sent for the invite to this module. Now, due to time constraints today, we will be completing the quiz review for quiz 3 on Thursday, first thing for module 4. We will have the quiz open today until 4:30, so please complete the quiz today to make sure you receive credit for today's module. Once you complete the quiz, you may exit the module for today.